Of the 6 remaining unsolved problems the Clay Mathematics Institute named as the most important questions of the millennium, there's famously one that nobody can explain at a dinner party. When Oxford mathematician Tom Crawford wrote up all 7 of the million-dollar problems, he opened the article on this problem by telling his readers to lower their expectations, as he warned that this is one of the hardest to explain in any terms, and that mathematicians can't even agree on what the problem is. Even the introduction to a 2001 lecture on the problem emphasized the unique difficulty of explaining it.
But I cannot imagine how tonight's problem, the Hodge Conjecture, can be explained to non-experts.
Welcome to Voyager, where we investigate the biggest unsolved mysteries in math, science, and engineering. In this video, I've tried my best to put together a story and explanation of the Hodge Conjecture. In 1907, a 23-year-old engineer named Solomon Lefschetz was working at a factory in Pittsburgh, Pennsylvania, when a transformer exploded. He survived, but he lost both of his hands. His career as an engineer was over, and so Lefschetz started over and decided to retrain in math, and specifically went on to complete a PhD in algebraic geometry. He is known for many advancements in topology, and students later told stories that he began his lectures by having someone wedge a piece of chalk into his artificial hand. Topology is the branch of math that studies the properties of shapes that stay the same when stretched, twisted, or bent. Instead of measuring distances, topology focuses on fundamental spatial features like connectivity and holes. The traditional joke about topologists is that they can't tell the difference between a coffee mug and a donut. Both shapes have exactly one hole, the center of the donut and the handle of the mug, and so they are topologically equivalent. By 1924, Lefschetz was well known for founding the field of algebraic topology, which bridged the worlds of shapes from topology and equations from algebra. And he described his own life's work with the now famous line that he had planted the harpoon of algebraic topology onto the body of the whale of algebraic geometry. Then, in 1930, a young Scottish mathematician named William Hodge published a paper that used Lefschetz's own topological methods to solve a problem on integrals on equation-defined shapes. But Lefschetz refused to believe it was correct, and he even insisted publicly that Hodge was wrong and demanded that the paper be withdrawn. When they finally met in person to settle the matter, the two mathematicians had fundamentally different views on how to approach the topology of algebraic varieties, leading to a period of armed neutrality and a reluctant invitation for Hodge to spend the next year at Princeton so they could work together. It took Hodge his entire first month at Princeton to convince Lefschetz that he was right. But once convinced, Lefschetz publicly admitted his error and praised Hodge's work. Through the 1930s and 40s, Hodge built his ideas into a full theory, which he called harmonic integrals, but is now known as Hodge theory. Hodge theory is a set of tools that show that the abstract wholes of a shape could be sorted into cleaner, more refined categories using ideas borrowed from calculus and physics. Hermann Weyl, one of the most influential mathematicians of the century, called it one of the great landmarks in the history of science in the present century. Then, in the summer of 1950, mathematicians from around the world gathered in Cambridge, Massachusetts for the International Congress of Mathematicians, the largest meeting in the field. And one of the invited speakers was William Hodge. His work had already helped shape the field of algebraic topology, and what he chose to present at the conference was an unanswered question. Are certain wholes, which show up as abstract quantities in topology, always produced by real geometric shapes described by algebraic equations? Hodge believed the answer to his question was yes, but he couldn't prove it. And 50 years later, still unsolved, the Clay Mathematics Institute announced this problem, now called the Hodge Conjecture, as one of the 7 most important problems of the millennium. The conjecture predicts that whenever a certain pattern of measurements show up in a shape, there is a hidden geometric cause sitting behind it. For many great unsolved problems, there's a general consensus that the hypothesis or conjecture is correct, and all that's missing is a formal mathematical proof. But here there's uncertainty about whether the Hodge conjecture is true at all. And adding to the confusion, even stating this question requires some understanding of topology, calculus, and algebraic geometry. I've stated a simple version, but what does it really mean? Before we get into what the conjecture actually says, this channel is supported by viewers on Patreon. If you want to help these videos get made, there's a link in the description. I also post there about what's coming next, and if you have a question about the topic, you can leave it and I'll answer it in a future video. Alright, what is the Hodge conjecture? The Hodge conjecture is a claim connecting equations and shapes. Formally stated by Pierre Deligne in the official problem statement, it's On a projective non-singular algebraic variety over the complex numbers, every Hodge class is a rational linear combination of classes of algebraic cycles. That's very complex, so let's build up to what that means slowly. In the 1600s, René Descartes had the idea of putting a grid of coordinates on a plane, so that every point is described by a pair of numbers. This is the Cartesian coordinate system. Now think of an equation as a test that points can pass or fail. Take the equation x squared plus y squared equals 1. The point where x is 1 and y is 0 passes the test, 1 plus 0 is 1. Now mark every point that passes. Together they form a circle, which is the shape of all its solutions. So the geometric shape is described by an algebraic equation. And the equations that the Hodge conjecture concerns are specifically polynomials, expressions built from the variables using only addition and multiplication, like x squared plus y squared or y squared minus x cubed. Now, we can also answer geometric questions algebraically. For example, how many times does one shape cross another? Start with the simplest version, a curve meeting a straight line. Take the curve y equals x squared minus 1 and ask where it meets the horizontal axis. We can answer it two ways. Looking at the graph, the curve intersects at 2 points. And solving the equation, we get the same answer. It's a second-degree polynomial, and so there are two solutions. And a line is a curve of degree 1. So really, we've just counted where one shape, a degree 2 curves, meets another shape, a degree 1 curve, and we see that multiplying the degrees of the intersecting shapes, we get the number of solutions. The highest power in a polynomial is called its degree, and if you try more examples, a pattern appears. A degree 3 curve intersects a line in 3 points, a degree 2 curve meets another degree 2 curve, for example, a parabola and a circle, in up to 4 points. Every time, the number of solutions is the 2 degrees multiplied together. So, mathematicians proposed a rule. A curve of degree n and a curve of degree m meet in exactly n times n points. But, change these examples just a little, and there seem to be cases where that rule fails. If you ask where y equals x squared plus 1 intersects the x-axis, now the graph of a degree 2 function doesn't cross the degree 1 function at all. And the algebra also fails because the solution must be a number whose square is -1. So, to make the theory continue to work, mathematicians introduced a new number, I. I is defined by the property that I squared is -1. And numbers built from I are called complex numbers and have a real and imaginary part. And once complex numbers are allowed, every polynomial equation of degree n has exactly n solutions, provided you count properly with a solution at a point of tangency counting twice. And this property is now called the fundamental theorem of algebra. But there's still a problem. According to the theorem, 2 straight lines, each of degree 1, should always cross in 1 point. They almost always do, but what about when the lines are parallel? There seems to be no intersection, which would violate the theory. But just like adding the imaginary number I, we can add one more number to the system that makes even 2 parallel lines intersect at 1 point. Starting with 2 intersecting lines, as you tilt one line gradually away from the direction of the other and watch the crossing point, it slides away farther and farther out. As you get closer and closer to parallel, this point gets closer and closer to infinity. And so the fix is to extend the plane. For each direction, add one new point, at infinity, a point that all the lines pointing in that direction share. And this is not an arbitrary invention either. It's what perspective drawing has always done, where 2 rails of a railroad track, parallel in reality, meet at a point on the horizon. And the first person we know of to write this idea down was actually not a geometer. In 1604, astronomer Johannes Kepler published a book on optics. And in it, he needed the family of curves you get by slicing a cone to behave as one family. And it only does if you allow a parabola to be an ellipse, with one of its 2 focus points being pushed infinitely far away. He called that the principle of continuity. And hold on to this idea that different conic sections, circles, ellipses, parabolas, and hyperbolas, are all versions of the same shape, because actually we'll come back to this in a minute. So each time there seemed to be a case that didn't fit the theory, the fix was to extend the space until the pattern of intersections has no exceptions. And the space, with these new points added, is called a projective plane, named for exactly that idea of perspective projection. In the projective plane, parallel lines meet at their shared point at infinity. And now with both complex numbers and the added points at infinity, there are no exceptions to the theorem, called Bézout's theorem, which states that a curve of degree m and a curve of degree n always cross in m times n points. And this completed space, complex coordinates plus the points at infinity, is called complex projective space. And this is the setting for the Hodge conjecture. But something challenging about this space is that we lose the ability to easily visualize shapes. The complex projective plane is two-dimensional over the complex numbers. That's why it's called a plane. But every complex dimension is made up of two real dimensions. One complex number has a pair of real numbers. So 2 complex dimensions is 4 real dimensions. Take the curve y squared equals x cubed plus ax plus b for fixed numbers a and b. Over real coordinates, it's a looping curve. But take the complete solution set, complex solutions and points at infinity included, and it's a surface, specifically a torus. This was Bernard Riemann's idea in the 1850s, that an equation of one variable in terms of another, taken over the complex numbers, is not a curve at all, but rather a surface. And we can create shapes of higher dimensions, use more variables and several polynomial equations at once, and the solutions live in complex projective space of n complex dimensions, which is really 2n real dimensions. And now that we've defined the space, the shapes we actually want to study are the solution sets in the space. The complete solution set of a system of polynomial equations is called an algebraic variety. And we want to look specifically at varieties that are non-singular, meaning smooth. Smoothness means if you zoom in on an arbitrary point, the shape flattens out. And so here we've defined a key term used in the Hodge conjecture. A complex projective non-singular algebraic variety really means a smooth shape built as the complete solution set of polynomial equations in the space where complex numbers and points at infinity are included. And once you have a variety, you can impose additional polynomial equations on top of the ones that define it. Each new equation carves out a smaller shape inside of it. For example, a curve lying on a surface. These shapes are called algebraic cycles. And now recall the conic sections, as this is the simplest case to explain the concept of cycles. A cone is a degree 2 equation. A flat plane is a degree 1 equation. If you slice the cone with a plane at different orientations, you can get a circle, ellipse, a parabola, or a hyperbola. But the cone has a sharp point at the top. And if you zoom in on that point and it never flattens out, that is a singularity. And while the Hodge conjecture only deals with non-singular varieties, the cone is still a good example for visualizing algebraic cycles. In the projective plane, the ellipse, the parabola, and the hyperbola are not 3 curves. They are one curve appearing 3 different ways relative to points at infinity. The ellipse does not include any points at infinity, but the parabola touches it at exactly 1 point. If you think of the 2 sides of a parabola as extending infinitely, they eventually become essentially parallel lines, and therefore meet and intersect at the point of infinity. And the hyperbola actually reaches infinity at 2 points, and those 2 points are the 2 asymptote directions. In a similar way, the 2 sides of a hyperbola that go in opposite directions actually connect in a loop at infinity. And over the complex numbers with the points of infinity, each of these curves is a sphere. As we just learned, a shape carved out of a bigger shape by imposing more equations is called an algebraic cycle. And so the conic sections are algebraic cycles on the cone. And these cycles are rigid, because every one of their points has to keep satisfying the 2 equations. So even though it seems like tilting the plane moves the curve freely, we can be precise about rigid means mathematically. If you were to draw a closed loop on the surface of a cone, it's unlikely to be rigid. The conic sections are rigid because they are cut out by another equation, the plane. A random generic loop drawn on the cone is not likely to be cut out by another equation, meaning there's no plane or other cone or any other polynomial surface whose intersection with the cone traces that exact curve. So rigid does not mean a cycle cannot be moved. It means that out of all the shapes sitting on that cone, only a very small family of them are cut out by other equations, like the intersection of the plane with the cone. So now this is starting to sound like the Hodge conjecture, and we're getting closer, but there are still a few more concepts to build up. Because the Hodge conjecture is also about topology, and topology deals with the opposite kind of shape, the kind that is allowed to deform and bend. A defining quality of a topological shape is the shape's holes. Remember the donut and the coffee mug example. So how do we define a shape's holes mathematically? If you draw a loop on a sphere, any loop, anywhere, it can slide and shrink down to a single point without leaving the surface. Think of the loop as a rubber band that can be stretched or deformed in any way, but can always be shrunk down to a point. In contrast, if you draw loops on a torus, there are two distinct loops that cannot be shrunk to a point and can never be transformed into one another. One loop wraps around the tube the short way, another wraps around the central hole the long way. Topology counts the loops that can't be shrunk, and that is the definition of a hole. So the torus has exactly two independent, one-dimensional holes, and those two loops are the evidence. And to clarify dimensions here, the loops are one-dimensional shapes because they have one degree of freedom. If you zoom in, you can only travel in one direction, and one-dimensional shapes define one-dimensional holes. But this idea can be extended to higher dimensions. A hollow sphere is a two-dimensional loop that detects a two-dimensional hole, and so on. On a shape of two n dimensions, there can be closed curves, closed surfaces, closed pieces of every dimension up to 2n. And just as we defined algebraic cycles, we can define topological cycles. Any such closed loop is called a topological cycle, but here two cycles count the same if one can be deformed into the other, and what's important is not any particular cycle itself, but its class. Everything a particular cycle could be deformed into. And the system that catalogs all of this is called cohomology. It is the complete inventory of a shape's holes. So let's contrast the cohomology ranks of the torus and the sphere to make this clear. And as a definition, rank is just how many independent classes sit in each dimension. Dimension 0 is the connected piece count. Both shapes, the sphere and the torus, are single connected pieces, so both have rank of 1. Dimension 1 is the loops, and this is where the shapes differ. The sphere has rank 0, because every loop shrinks to a point and detects no hole. The torus, however, has rank of 2, because two of its loops can't be shrunk and detect different one-dimensional holes. And then dimension 2 is the enclosed cavity. Both have rank of 1. The sphere's surface wraps around its interior and can't be collapsed, and the torus is hollow too, so its surface does exactly the same thing and detects the cavity inside the tube. Now let's connect the algebraic and topological cycles. Algebraic cycles are special cases of topological cycles, specifically those that are rigidly defined by polynomial equations. That means that every algebraic cycle already exists in the cohomology inventory. So if someone hands you a topological cycle, can it be deformed until it is exactly on an algebraic cycle, a shape cut out by equations? Sometimes, obviously not. Complex equations only ever create shapes of even dimension, since every complex degree of freedom is two ordinary ones. So a one-dimensional topological cycle, like the loop on a torus, can never be deformed into an algebraic cycle. And this seems counterintuitive at first, because a circle has an equation. We wrote it earlier, x squared plus y squared equals 1. So how can this circular loop not be algebraic? Look at what the equation actually solves for. On Cartesian coordinates with real numbers, the equation draws a circle. But we're not on the page anymore, we're in the complex projective plane. Once we allow complex numbers and add the points at infinity, the complete solution set isn't a circle, but rather a sphere. So a one-dimensional loop, like the one going around the torus, is not a complete solution set. It's a slice of a solution set where the imaginary part all happens to be 0. More clearly, we're not looking for whether a loop has an equation. It does. The question is whether any equation cuts out the loop alone. And no equation does in this space. The smallest equation-defined shape containing that loop is the entire sphere. That's what it means for a cycle to be algebraic. Not that it satisfies an equation, but that equations cut it out. So among only the even-dimensional classes, which ones actually contain a shape cut out by equations? We've defined a class as everything a cycle can be deformed into. So a class is an infinite collection of shapes. And the question is, does that class contain an algebraic cycle? An easier way to answer this would be to represent each class with a single object, and then look for properties that a shape defined by an algebraic equation must have. And to do that, we need to bring in calculus. In geometry, calculus is a tool for measurement. To find the length of a curved path or the area of a curved surface, you can integrate. You can add up infinitely many infinitesimal contributions. And the objects that can be integrated are called differential forms. We can visualize this relationship by imagining a river where the water's velocity at any given point is represented by a vector arrow, and a fishing net dropped into the water acts as the differential form. If the net is placed perfectly perpendicular to the river's current, the maximum amount of water passes through the mesh. If you tilt the net at an angle, the effective opening facing the current shrinks by the cosine of that angle, reducing the total flow caught by the mesh until the net is turned completely parallel to the flow, at which point the water flows past entirely and the measurement drops to zero. In calculus, this tilting process is captured by feeding the components of the river's velocity vector into the differential form, which algebraically weights the flow across the coordinates. And this framework reveals a powerful topological property. If you stretch two different nets across the same river and anchor them at the exact same spot on the opposite banks, the total water passing through both nets will be completely identical, regardless of whether one net is stretched taut or loose and wrinkled. Every drop of water crossing the first net must eventually cross the second, meaning the actual geometric shape of the net does not matter for the final calculation. In the language of differential geometry, this independence of shape indicates that the two nets belong to the same topological class, known as a de Rham cohomology class. But this topological equivalence breaks down when a physical obstruction, like a rock, is placed in the middle of the river, introducing a topological hole into the fluid space. If you anchor one net on the left side of the rock and one on the right side, the two nets will capture different portions of the river current, and you can't morph one net into the other without changing the endpoints or tearing it across the rock. This phenomenon is described by the generalized Stokes theorem, which states that the integral of a differential form over the boundary of a region equals the integral of its exterior derivative over the region itself. In a smooth, continuous river, with no water magically appearing or disappearing, the exterior derivative of the flow form is zero everywhere. When no rock is present, the space between the two separate nets forms a valid continuous region, allowing Stokes' theorem to prove that the difference between their measurements is exactly zero. However, when the rock is introduced, because you cannot draw a continuous flow region across the solid rock, Stokes' theorem cannot bridge the gap between the left and the right channels, formally proving why the presence of a topological hole splits the space into distinct, non-equivalent classes of differential forms. And so we saw how forms are a useful construction in topology because the integral does not change even when the loop is deformed. The value you get from integrating only depends on the loop's class. So the number doesn't belong to a particular cycle, but rather is a single number that depends only on the class. So the entire catalog of a shape's holes can be rewritten in the language of calculus. But the forms detecting a given class make up an infinite family, all equivalent as far as that class is concerned. And this is where Hodge's contribution comes in. On a projective variety, there is a natural way to measure distances and angles, and Hodge proved that with it, each family of forms contains exactly one canonical representative called a harmonic form. So the entire whole inventory of the variety can be rewritten in calculus because every class has exactly one harmonic form which can be integrated to describe the entire class, and every harmonic form belongs exactly to one class. And more importantly, a form is a concrete object, which means you can operate on it. Instead of thinking about complex numbers as only extending the number line, think of them as encoding rotation. Multiplying by I turns the plane a quarter turn. 1 becomes I becomes -1, -1 becomes -I, and a fourth multiplication returns to 1. A complex variety, therefore, has rotations built into every one of its complex directions. And what's important is that rotation does not change measurement. It doesn't change length, area, or volume. But it does change forms. And most forms are changed by a scaling factor. And that factor is the information that sorts the forms according to how they respond to the rotation. Let's take a closer look at what that factor is. In each complex direction, there are two ways to turn, with the rotation or against it. And a form is assembled out of both kinds of pieces. So we count them. Call P the number of pieces that turn with the rotation, consider these dz, and Q the number that turn against it, consider these dz bar, meaning the complex conjugate. Each with piece adds e to the I theta. Each against piece adds e to the minus I theta. Multiply them together and the whole form comes back scaled by e to the I times p minus q theta. So as you go around the angles from 0 to 2 pi, the factor gives p minus q. So what the rotation gives us is the difference between these two numbers, p minus q. and that difference is what the factor records. The rotation shows how balanced or unbalanced P and Q are, not the two numbers themselves, just the gap between them. But that's enough because the degree of the form, how many dimensions the shape it measures has, is P plus Q. So the dimension gives you the sum and the rotation gives you the difference, and the two together tell you P and Q exactly. Thus, the inventory of each dimension can be split into pieces, each one labeled by their own pair P and Q. And this sorting is called the Hodge decomposition. And within the decomposition, there are special cases where P equals Q. Here, the difference is 0 and the rotation does not change the form. These are called balanced classes, labeled type P, P. And remember that the dimension of a class is P plus Q. So if P equals Q, the dimension is 2P, which is always even. And that matches what we said earlier. Algebraic equations only ever cut out shapes of even dimension. So why do the balanced classes matter? Go back to the integration, and this time just count directions. Take a form and integrate it over an algebraic cycle. An algebraic cycle is a shape cut out by complex equations, so it's a complex shape, and integrating over it amounts to measuring complex volume. And we just said that rotation doesn't affect measurement. Turning a shape doesn't change how big it is, so the answer can't move when the rotation is applied, which means the class of an algebraic cycle has to be one of the classes the rotation leaves alone. It has to be balanced type P, P. And there's a second thing every algebraic cycle satisfies. An algebraic cycle is an actual shape sitting inside the variety, and so you can only have rational combinations of them. Cohomology in general is willing to combine classes using any numbers at all, including irrational ones. But a class that comes from real shapes is assembled by counting, so it only needs rational numbers, whole numbers, or fractions, since there is no way to have an irrational number of actual items. So now we have two tests we can apply to any class in the inventory. Is it rational? And is it type P, P, meaning untouched by rotation? A class that passes both is called a Hodge class. And we've just shown that every class coming from an algebraic cycle passes both. So a Hodge class is a whole that looks like equations made it. But are these two tests enough? Look at it the reverse way, and finally, we've arrived at the Hodge conjecture. If a class is rational and type P, P, is it always built out of actual algebraic cycles, a combination of real shapes cut out by real equations? That is the question Hodge put to the International Congress in 1950. And his conjecture is that the answer is yes. Informally, is every whole that looks like it was made by equations actually made by equations? Formally, in the words of the official Clay Prize statement, on a projective non-singular algebraic variety over the complex numbers, every Hodge class is a rational linear combination of classes of algebraic cycles. And what's interesting is that without each of these words, the conjecture is actually proven to be false. Interestingly, there's also one case of the Hodge conjecture that is known to be true, the case where P equals 1. And this was actually proven in 1924, several years before Hodge even published anything, by Solomon Lefschetz. And so now that we've finally understood the full statement, where do we go from here? How do mathematicians test the conjecture? To check whether a class is a Hodge class, you can use calculus to compute harmonic forms, rotations, and factors. But the conclusion is about geometry. It promises an actual object carved out by actual polynomial equations. The conjecture claims that a calculation guarantees a shape. Hodge classes turn up everywhere, but there's no general procedure that takes a Hodge class as an input and hands back the equations of the cycle that fills it. The conjecture states that the shape is there, but we haven't discovered a general way to find it yet. And this conjecture is so hard to grasp, both because it's impossible to visualize for anything more than the trivial case, and it's so far removed from the everyday world. So what does this mean in real life? I'm going to leave that question for the next video. But in the meantime, if you like this introduction to the Hodge conjecture, subscribe. On this channel, I investigate unsolved questions in math, science, and engineering, and I think you also might like my recent video on another one of the unsolved Millennium Prize Problems. It's on screen now. Also, if you have a question you'd like to see answered in a future video, check out my Patreon where you can see what's coming next and support the channel. The link's in the description. I'll see you in the next one.